Okay, so welcome. In today's lecture, we're just going to sort of look at a few more examples of some more complicated Laplace transforms so that we sort of have more to work with, can solve more complicated problems. So to start off, so just to remind a couple formulas where we learned in the previous lessons, these few couple formulas, sort of this one is kind of going to be immediately the most important one. And then we have the linearity property, and the one we learned in the last lecture is this t domain. So if we have the derivative of a function, we can find its Laplace. We can express the derivative in terms of the normal Laplace transform. Okay. So let's look at another example. So we know what the formula for t is. We know what the formula for e to the at, but what happens if we do something like this? So we take the product of the two. So one thing to note, the answer is not going to be just the product of the things. We might be able to add and add together solutions, but we cannot multiply together solutions. Okay. Okay, but if we expand this using the definition, not 0 to t, but 0 to infinity of t, e to the at, times e to the negative st. And we'll rewrite that once. T, and then we'll just combine the exponents. So e to the a minus s times t dt. Okay, and now we're going to do a partial fraction, as you're hopefully getting used to by this point. So if we set our u to be t, then our du is just dt. Our dv is going to be e to the a minus s times t. It's going to make this e to the a minus s times t over a minus s. So then we have that for our first term minus the integral from 0 to t of our v times du, which is just that. So we have e to a minus s times t over a minus s dt. Okay, so sort of one thing to note, again, if we take this limit, right, we're going to need a minus s to be less than 0, which tells us that a is less than s, or s is equal or greater than a. But if we have that, then when we plug in infinity, or we take the limit rather, we're going to get 0, and then minus 0 e to the 0 over a minus s. So that whole term just becomes 0. Over here, I can pull out that a minus s because it doesn't have any t's in it. So I'll pull it out and flip it around, s minus a, canceling with a negative. And now we have, limit big T goes to infinity, that e to the a minus s times t over a minus s, or yeah, that's it. Again, integral of this, just going to divide by a minus s. Looking here again, sort of note we need the same thing. Oh, I forgot the t value. We need the same thing to be true. We need s to be greater than or equal to a. And but if we have that, right, then we'll get limit 1 over s minus a. That first term is going to be e to the negative infinity, so that's just going to go to 0 over a minus s, and then minus e to the a minus s 0 over a minus s. And canceling that, pulling that out, we get that our final answer is 1 over s minus a squared for s greater than a. Okay, so there's our final answer there. And you may sort of notice that this was, kind of very similar process to when we computed the Laplace transform of just t. Really, the only change once we sort of get here is, and now instead of s, all these sort of places I'm underlying in red, we have a minus s. And this is actually part of a larger sort of pattern that is going to be really helpful in identifying some sort of Laplace transforms and in computing them. So this is what's known as the shift formula, though I guess I should say S-domain shift, technically. And what this lets us do is compute the Laplace transform of anything that we know the Laplace transform of times an exponential. So let's see what we get. So we'll just write down the definition. And I'll combine them. This time I'm going to pull the negative out. So I'll do negative s minus a times t. And I would see now that, okay, let's say, the Laplace transform of f of t, again, is negative f of s. So if let's say I say let, p equal s minus a, then this thing is going to be the same from 0 to infinity of f to the t, e to the negative p times t dt. Okay, well, if we look here, this is just the Laplace transform of f, really, except we have a negative p instead of a negative s. So that has to equal negative p. And now if we undo the substitution, we get that we just get s minus a. So the Laplace transform of anything that we know times e to the at is just the Laplace transform of f with s minus a plugged in instead of s. Okay, so let's take a look at this and just compare it to some of our previous things. Okay, so we already knew that t times the Laplace transform of t is 1 over s squared. And now this sort of new rule says that the Laplace transform of t times e to the at is just the Laplace transform of t, which is 1 over s squared, except I'm replacing s with s minus a. And if we look at that, we see that is exactly what we got. So yeah, it's a really useful thing. Means that having something multiplied by an exponential means it's really not that bad. Okay. So another example, let's compute the Laplace transform of t squared. So this was one that was actually appeared on the worksheet for our Zoom meeting, but so let's sort of do it via the method there, and then I'll mention another way. So the Laplace transform of t. So normally to solve this, we would actually have to do a double integration by parts, which, I mean, integration by parts, I think you guys give it too much of a bad rap, but a double integration by parts, it's getting a little bit much. So we still have to do one, but then we're going to use a shortcut, just sort of like we did on the worksheet, by identifying something as something we already know. So our u is t squared, our dv is e to the negative st dt. du and v is e to the negative st divided by negative s. So we'll write this. So we have t squared e to the negative st over negative s. Minus the integral from 0 to infinity of 2t divided by negative s times e to the negative st. Okay, so again, we'll sort of look at this part here, see what's going to happen. Again, we'll sort of notice that s needs to be greater than 0 so that we get negative infinity, not positive infinity, which would blow up. And then we would have, the limit as t goes to infinity of capital T squared e to the negative st over negative s minus 0 e to the 0 over negative s. Over here, we pull that out, so 2, and then over negative s, I'll just make that a positive. We can see that everything in this limit goes to 0. And now I want you guys to note that this guy is just the Laplace transform of t. So we get the Laplace transform of t squared is 2 over s times the Laplace transform of t, which remember we just saw is 1 over s squared. So if we simplify, get the Laplace transform of t squared is 2 over s cubed. Okay, so now let's sort of jump ahead a little bit. So we can look at the Laplace transform of t to the nth power. So a lot of these steps are going to be the same, as we'll sort of see. And at the end, I'm only going to use one integration by parts, but I'm not going to get a final answer exactly. So again, u is t to the n, du is n, t to the n minus 1. Oops. So t to the n e to the negative st over negative s times the integral from 0 to capital T, and then minus integral from 0 to infinity of n t to the n minus 1 times e to the negative st divided by negative s. And I think I do have to make one assumption on n here. We have to say it's greater than 0. Okay, so similarly to above, this whole thing is going to go to 0 as long as s is greater than 0. So it's very similar, but we can just sort of notice, okay, yeah, that's going to go to 0. So we get 0 for that whole thing, and then minus this guy over here. I'll pull out the n and the negative s. And I can see if I cancel that, I get n over s, and then this guy, t to the n minus 1 times e to the raised to the negative st power. Well, that's just the Laplace transform of t to the n minus 1. So we have that this is n over s times the Laplace transform of t to the n minus 1. Okay, so we already sort of know a couple examples of this. So just as sort of a separate case, we know that, if we have t to the 0th, right, that's the same as the Laplace transform of 1. And we sort of know that this gives us 1 over s. Similarly, Laplace transform of t is 1 over s squared. We've already seen that. Laplace transform of t squared is 2 over s cubed. And now the first one we haven't computed yet, t cubed, well, that's going to be 3 over s times the Laplace transform of t squared, but that's just 3 over s times 2 over s cubed, which gives us our answer 6 over s to the fourth. Similarly, t to the fourth is going to be 4 over s times the Laplace transform of t cubed. So that's 4 times 6 over s times s to the fourth. So we're going to get 24 over s to the fifth. Okay, so you might also recognize these numbers in sort of a different way if I don't actually do the products, right? So I have 1 over s squared here. Here I have really 2 times 1 over s cubed. Here I just multiplied by 3, so 3 times 2 times 1 over s to the fourth, and 4 times 3 times 2 times 1 over s to the fifth. Now what I can see is that the Laplace transform of t to the n, right, these numbers have a particular name. So n factorial, right, is the product of the numbers 1 times 2 times 3 all the way up to n minus 1 times n. And so this is just n factorial divided by s to the n plus 1. And so this is sort of a rule for powers of t for the Laplace transform. All right, I'm going to note one other sort of property, and this is what we're going to call the S-domain derivative. So this sort of asks, okay, what happens when I take the derivative of the Laplace transform? And so let's see what happens. So s and t here are sort of separate variables. So unlike a lot in this class, and I know this confused some people, right? We usually have two variables like a y and a t in a problem, but we can't just like integrate t ignoring y because y is a function of t that we're trying to solve for. Well, in this case, t and s are truly separate functions, and so I can just take the partial derivative with respect to s, and it doesn't matter, right? Just like it doesn't matter what order I integrate things if I have truly separate variables. It doesn't matter if I integrate and then take the derivative or take the derivative and then integrate. So if I take the partial derivative with respect to this, right, note that I can ignore the f of t, that's basically a constant, and I'm just asking to take the partial derivative of e to the negative st with respect to s. We know how derivatives of exponents work. We're just going to multiply by negative t. right? And so I get my sort of answer here that, so if I take the partial derivative with respect to s of this, so I get f prime of s is equal to the Laplace transform of a negative t f of t. And if I just move the negative to the other side, I get the Laplace transform of t times f of t is negative the derivative of f of s. Okay, so let's just sort of use this to compute something in another way. So we can use this to sort of check our answer up here, and also sort of use their answer up here to check this, right? So I know that the Laplace transform of t is 1 over s squared. And this says that the Laplace transform of t times t is the derivative of 1 over s squared. So remember, derivative rule, bring down the exponent, negative 2, or I'm sorry, it's negative the derivative of that. So just put in minus out front. So minus negative 2 s to the negative 3. Negatives cancel and become a plus, and we have 2 over s cubed. So this is another way to sort of see that thing, but it also is, you know, useful for a few other cases. All right, now let's look at trig functions. All right, so I want to first sort of make a note. This, you could totally proceed with this in a very sort of standard way that you've done, sort of learned in Calc 2. But again, it would involve you know, 2 integration by parts. And it's the thing where you do 2 integration by parts, and then you get the same thing again, and then you move it over to the other side and solve. And that's not really fun. So what we're going to do is use Euler's formula again. So remember that Euler's formula said that e to the it was cosine of t plus I sine of t. And a sort of related thing, if instead I make this negative, well, I just get cosine negative t plus I sine negative t. But remember that cosine of an angle is the same as the cosine of the negative, and sine of a negative is the same as the negative of the sine. So I have sort of this formula and this formula. And so what happens if I add these two things together? Well, I just add the top to the bottom. So I'm going to get 2 cosine. And then I add I sine of t and negative I sine of t. So plus, I times 0, which is still just 0. So I get 2 cosine is equal to e to the it plus e to the negative it. So dividing by 2, I get that cosine of t is equal to e to the it plus e to the negative it over 2. And sort of similarly, if instead of adding I subtract the two equations, I would get that sine of t is equal to e to the it minus e to the negative it divided by 2 times I. So these are going to be really useful because we can now just use some properties of the Laplace transform that we already know to compute these integrals. Okay, well, if I just expand this as the Laplace transform of e to the it plus e to the negative it divided by 2. And then remember, linearity says I can pull out that 1/2 and split up the sum. And now I can use my rule for exponents, which says, right, Laplace transform of e to the at is 1 over s minus a. So I'm going to have 1/2 1 over s minus I plus 1 over s minus negative I and so that's going to become s plus y. I can choose a common denominator. And if you look at what our denominator becomes, we should end up with s squared minus I squared I squared, of course, is -1. So s squared minus -1 is just s squared plus 1. And on the top, we have 2s because the i's cancel. So what this means is that the Laplace transform of cosine of t is just s over s squared plus 1. All right, so I tried to be, real careful with that. Of course, at a certain point, you're just going to need to know the formula. And sort of, similarly, I'm not going to work this one through because it's essentially the same. But we can get that the Laplace transform of sine of t, right, is using that same formula e to the it minus e to the negative it divided by 2i. But at the end of the day, you will end up with 1 over s squared plus 1. And of course, there's different ways of seeing that now. We could also use the fact that that sine is negative the derivative of cosine and compute it that way. So sort of lots of different ways to compute these different things once we know a couple. All right. So let's see. So just, I guess I'll do one more property of the Laplace transform. So this is going to be just scaling. I would say it's S scaling, S domain scaling, or T domain scaling, but they're so similar that I'm just going to call the whole thing scaling. So let's look at what happens when we compute the Laplace transform of f, times a of t, where a is just some constant. Okay, so I mean, if I just sort of proceed forward, I can't really do anything, but sort of my goal is, right, to express this in terms of the Laplace transform of f. So what I'm going to do is I'm going to let x equal a times t, which of course means t equals x over a, and dx equals a dt, or dt equals d to the x over a. Okay. So now I get the integral from 0 to infinity of f of x times e to the negative s, and now I got to use x over a there. And now this dt can become dx over a. And I'm just going to rewrite this one more time. So I'm going to pull out the 1 over a. I'm going to combine that a with the s term. And then I see that what I get is the Laplace transform of fat is equal to 1 over a times this, which is the Laplace transform of f, but instead of s, I'm using s over a. I'll note that similarly, if I instead have the Laplace transform scaled, then what I end up getting is the inverse Laplace transform of this is 1 over a times f of t over a. So it's really sort of the same formula, just s and t are swapped. Okay. So I'm just going to leave you guys with an exercise. Or two of them. So for the first one, and so use Euler's formula for this. And for the second one, so using any formulas and t domain shift, and S domain derivative. So for the first one, compute the Laplace transform of e to the 6t times sine of 2t. And of course you can use your answer from number 1 in there. For part B, we're going to compute the Laplace transform of t times, let's say, sine of 2t. Or actually, let's just do t times sine of t. Yeah, that's good. All right, so give those a shot. Now I will briefly sort of cover the answers. So remember, for this, the formula we're using is sine of 2t is e to the it minus, or I guess if it's 2t, it would be e to the I 2t minus e to the negative I 2t all over 2I. So if we compute the Laplace transform of sine, we should have 1 over 2I. We'll just pull that out, and then adding these things together. So 1 over s minus 2I minus 1 over s plus 2I. And now we're not done. We need to sort of make sure that this is back in sort of real form. But at the end of that, what we should get is 2 over s squared plus 4. Using that answer, this answer is now very clear. We just take that s and replace it with s minus 6. Right, because the shift formula says Laplace transform of e to the at times f of t is the Laplace transform of f, but replace s with s minus a. Similarly, using the s domain derivative rule, we have that this is equal to the derivative of our Laplace transform of sine of t. I'm sorry, negative the derivative. And so this becomes negative the derivative of 1 over s squared plus 1. Taking the derivative of that is going to be negative 1 over s squared plus 1 squared times 2s. And so we'll get as our answer 2s over s squared plus 1 squared. All right. And I will stop it there.